What if the volcano that exploded in 1980 is waking up again? After decades of quiet, Mount St. Helens is showing signs of movement deep below. A silent warning that it may not be done yet.
Mount St. Helens erupted, killing 57 people. Como's Theron shows us the advice from local emergency teams to make sure we are prepared for the next cascade eruption.
What if I told you that the same volcano that tore itself apart in 1980 has begun to move again, silently and from within? For more than 4 decades, Mount St. Helens has been a laboratory for volcanologists, a wound in the earth watched by hundreds of sensors. Its catastrophic 1980 eruption destroyed 230 square miles of forest and lowered its summit by over 1,000 feet. Since then, the mountain has rebuilt slowly, extruding domes of lava, breathing steam, and pretending to sleep. But in late 2025, something changed. New INSAR satellite data revealed subtle ground motion, an oval of uplift spreading across the volcano's southern flank. Within months, seismic arrays detected rhythmic, low-frequency tremors, too deep for rock fracturing, too regular for randomness. At first, scientists dismissed it as post-glacial relaxation. Then came the gases. A sudden surge in carbon dioxide and sulfur dioxide from vents near the 2004 lava dome. These readings matched ratios seen only when magma rises toward the surface. The mountain that once roared without warning is now stirring in silence. What they've detected beneath Mount St. Helens has left even seasoned researchers uneasy. Chapter 1: Mount St. Helens' Hidden Chamber. What if the magma chamber beneath Mount St. Helens isn't one body, but 2, linked like lungs beneath the crust? Seismic tomography, Earth's version of X-ray vision, has revealed a dual-layered system below the volcano. The first sits about 7 kilometers deep, a pocket of semi-molten rock roughly the size of Seattle. The second lies more than twice as deep, feeding it from the mantle through a narrow conduit. For years, this deeper chamber was thought dormant, sealed after the 2008 lava extrusion. But in 2024, new P-wave velocity maps showed its boundaries shifting, as though molten material were migrating upward again. By spring 2025, GPS stations around the summit began rising by 3 to 5 millimeters per month, a tiny motion, but unmistakable. Inside the USGS Cascades Volcano Observatory, the conversation changed. "It's breathing again," one geophysicist said quietly. This layered magma system explains the mountain's unpredictability. When the lower reservoir feeds the upper without release, pressure builds invisibly. The last time that balance failed, the northern flank collapsed in the most devastating landslide in US history. Now, the sensors are hearing the same deep pulse once more. Slow, rhythmic, persistent. Recent magnetotelluric imaging supports the seismic data, revealing a conductive pathway extending towards the surface, like a vein awakening after years of dormancy. Gas emissions from the crater have subtly changed too. Higher sulfur dioxide levels, a telltale sign that magma is degassing below. Even the mountain's hydrothermal vents, those steaming fractures across the crater floor, are louder than they have in a decade. To the untrained eye, Mount St. Helens appears serene, capped in snow and silence. But beneath that frozen calm, magma may be stirring in tandem chambers, 2 hearts beating below the surface. If the upper one fills faster than it can vent, it could trigger another catastrophic dome collapse, or even a lateral blast. Scientists aren't predicting an imminent eruption, but they're watching. Every tremor and microquake charted, every tilt and rise recorded. The mountain's pulse has returned, and it's growing stronger with each passing month. Chapter 2: Mount St. Helens rising heat. Deep beneath the crater floor, temperatures are climbing. Thermal infrared data from NASA's ASTER satellite shows a steady heat increase around fumaroles once thought extinct. Steam that used to drift lazily now jets in bursts. Geologists trekking across the pumice plain in early 2025 found vents ringed with new sulfur crystals, bright yellow against ash-grey stone. Gas chromatography tests revealed elevated CO2/SO2 ratios, the unmistakable sign of magma rising into the shallow crust. And yet, there are no surface quakes, only tremors too deep to shake the ground. That's the deception of Mount St. Helens. It hides its strength until the last possible moment. Like a pressure cooker sealed beneath ice, its energy builds in silence. Beneath the crater, temperature gradients now exceed levels last seen in the early 2000s, and newly installed borehole thermometers show a 6 degrees Celsius rise in just 6 months. The volcano is literally heating from within, even as snow still blankets its rim. The USGS calls this stage magmatic intrusion without eruption, a slow inflation that can last months or decades. But history remembers how fast that status can change. In March 1980, the same pattern unfolded. Small bursts of heat, minor degassing, and a deceptive calm that lulled observers into thinking the worst was over. Then, on May 18th, the mountain tore itself apart in a single, sideways explosion that leveled 600 square kilometers of forest. Today, seismometers are picking up long-period tremors again. Those low, rolling waves that indicate magma movement rather than tectonic breakage. Combined with heat flux anomalies and gas data, they paint a chilling picture. The volcano's plumbing is pressurizing. No one is predicting a repeat of 1980, but as thermal maps brighten and the air above the crater thickens with vapor, scientists can't shake the feeling that Mount St. Helens is, once again, gathering breath before it speaks. Chapter 3. Mount St. Helens' Silent Swarm. What if earthquakes were no longer violent jolts, but musical notes played by magma itself? In February 2025, seismographs recorded over 700 tiny tremors beneath the volcano in less than 3 weeks. Most were too faint for human detection, clustered at depths between 10 and 15 kilometers. When their waveforms were filtered, they revealed harmonic structure, oscillations repeating like the vibrations of a bowed string. This volcanic tremor is often the prelude to fluid movement within a conduit. In Iceland, similar patterns have preceded eruptions by months. But at St. Helens, the tremor grew stronger, then abruptly stopped. To the scientists watching live feeds from the Pacific Northwest Seismic Network, it was as though someone had muted an orchestra mid-performance. Instruments that once danced with rhythmic motion fell eerily flat. Such silence unsettles scientists more than the noise. It can mean the magma found a new pocket to rest, or that it's sealing itself in, pressure mounting behind walls of rock. When magma halts suddenly, gases trapped within begin to accumulate, changing pressure dynamics inside the chamber. This process can transform the system from fluid and flexible to brittle and explosive. Researchers analyzing the data noted a subtle shift in wave velocity ratios between P waves and S waves, suggesting partial melts solidifying in key pathways. It's the geological equivalent of a blocked artery. Temporary stability, masking growing risk. Satellite deformation data, meanwhile, shows a minute but measurable sagging of the southern flank, implying that something beneath may be expanding or redistributing mass. Seismologists now refer to this phenomenon as the pause before the pulse. It's a stage of deceptive calm, where the volcano seems to rest, but is in truth reorganizing its internal network. Whether that reorganization leads to relief or to rupture remains unknown. The instruments are still listening, waiting for the mountain's next note. Chapter 4. Mount St. Helens Breathing Dome. What if a volcano could breathe, and every breath brought it closer to waking up? Atop the 2004 lava dome, a team of geodesists installed high-precision tilt meters, devices that detect the slightest flex in the Earth. By June 2025, the readings showed something subtle yet extraordinary. The dome was rhythmically rising and falling by a few millimeters every 36 hours. It was as though the volcano were breathing. Gas emissions followed the same pattern, surging and fading in sync with the tilt data. Scientists believe these oscillations are caused by magma pulses expanding gas pockets beneath the dome. Each exhale releases pressure. Each inhale draws in silence. The cycle mirrors respiration, an alternating rhythm of strain and relief that hints at a living system balancing itself against collapse. Thermal cameras confirm the pattern. Infrared readings from both drone surveys and the Aster satellite show periodic warmth spreading across the dome's upper face, followed by cooling phases that align almost perfectly with gas emission data. It's not enough to suggest imminent eruption, but enough to prove that molten material is moving in measurable cycles just below the surface. To volcanologists, this breathing represents a delicate equilibrium. The dome acts like a valve, absorbing the internal expansion of gases, then flexing outward to vent small amounts before retreating again. But that balance is precarious. If a blockage forms, say a solidified plug of viscous dacite, the mountain's breath could catch, building pressure until it breaks through violently. From the crater rim, nothing appears unusual. Wind sighs across ash and snow. The landscape seems frozen in time, serene and still. Yet inside the data, Mount St. Helens is very much alive. Its breath deep, deliberate, and patient. The mountain may not roar today, but every rise and fall of its dome is a reminder that life, even in stone, follows a rhythm all its own. Chapter 5. Mount St. Helens Expanding Reservoir. What if I told you that Mount St. Helens magma chamber is growing again, slowly, silently, and from the depths upward? Deep Earth tomography and gravity inversion models show that the shallow magma body beneath St. Helens has expanded by almost 0.8 cubic kilometers since 2018. That's equivalent to hundreds of millions of tons of molten rock. This increase is not caused by eruption or lava flow. It's inflation, magma accumulating at depth without release. As it pushes upward, the crust above bends, storing potential energy like a drawn bow. Field teams from the Cascades Volcano Observatory have confirmed the deformation using high-resolution GPS networks installed around the crater rim. Stations several kilometers apart are now moving subtly away from each other, an unmistakable sign of internal pressure. Laser ranging instruments and satellite-based radar interferometry, INSAR, corroborate the same trend. A slow, dome-shaped uplift spanning nearly 12 kilometers across. But what makes this discovery so alarming is the depth. The expansion is taking place around 13 kilometers below the surface, well beneath the zone that produced the 1980 and 2004 eruptions. This depth places it within the transition layer between brittle crust and ductile mantle, an area capable of storing immense energy before failure. In other words, it's the perfect pressure trap. Geophysicists suspect this growth may not be isolated. Beneath St. Helens lies a vast, partially molten region that could connect with neighbouring magmatic systems along the southern Cascades. Some models even hint at a lateral corridor extending toward Mount Adams, an underground artery feeding heat and material upward through cracks in the subducting Juan de Fuca plate. For now, the pressure remains contained, but containment has limits. The longer magma collects without venting, the more stress accumulates on the rocks that hold it in. Should that barrier rupture suddenly, the release could be violent and unpredictable. As one scientist noted quietly during a recent USGS briefing, The question isn't if it's moving, the question is when it stops being patient. And as each day passes, Mount St. Helens' reservoir continues to swell, an invisible heartbeat echoing beneath the Pacific Northwest.
Chapter 6.
Mount St. Helens' forbidden gases. What happens when magma begins to breathe the air of the living world again? In late 2025, gas monitoring drones hovering near the crater captured something unexpected. Sharp bursts of hydrogen and methane in ratios that shouldn't exist in a magmatic system. Normally, volcanic emissions are dominated by water vapor, carbon dioxide, and sulfur dioxide. Hydrogen and methane indicate reactions between magma and buried organic sediments, a chemical process that only occurs when molten rock encounters water-rich carbon layers deep below. That means the magma may have already reached strata never touched in living memory. Beneath Mount St. Helens lies a complex network of ancient lake beds and glacial sediments, fossilized remnants of an ecosystem buried thousands of years ago. If rising magma has begun to melt through these layers, it could be generating volatile gases at an accelerating rate. If magma is interacting with groundwater and carbon deposits, the result can be explosive. Superheated water flashing into vapor, shattering rock, and releasing a blast wave that traveled faster than sound. Thermal cameras confirmed transient hotspots along the crater's southern rim, consistent with gas seeps forming through microfractures. Local pilots have reported faint plumes rising at dawn, steam that vanishes by noon but leaves sulfur traces in the air. Some of these plumes align with new fissures identified by INSAR data, forming a subtle crescent pattern that may mark the path of migrating magma. USGS chemists analyzing the airborne data call these hydrogen-methane spikes forbidden gases because they break the expected chemical balance of a sealed volcanic system. Their presence suggests the volcano's plumbing is no longer isolated. It's probing higher, mingling with the crust's volatile, rich layers. The gases tell a story the instruments cannot hide. Magma is testing the surface again.
Chapter 7.
Mount St. Helens' memory of fire. What if the mountain itself could remember every explosion, every tremor, every scar it ever bore? What if I told you that the rocks inside Mount St. Helens still remember every eruption that's ever shaped them? Petrologists analyzing crystal samples from the 2004 dome discovered microscopic bands, alternating layers of glass and mineral formed by pulses of magma over centuries. These bands record pressure, temperature, and chemistry like tree rings. Each layer is a frozen moment of chaos, a chemical memory of the volcano's heartbeat. When compared to new samples collected in 2025, something remarkable appeared. The same pattern was repeating. The ratio of trace elements, the order of crystallization, even the trapped gas bubbles, all identical to the pre-1980 stage. It's as if the volcano's internal laboratory is running the same experiment all over again. The magma mixing, the degassing, the slow compression of pressure, it's all echoing the buildup that once led to catastrophe. In other words, the mountain's internal chemistry has reset. The volatile balance between silica-rich and basaltic magma, the delicate layering of pressure and heat, all mirror the conditions that preceded its last major eruption. This doesn't guarantee a repeat of 1980, but it proves one thing. Mount St. Helens is cycling, not dying. Every rise and collapse, every breath of gas and plume of ash leaves a signature in its rocks, and those signatures are back. It's as though the volcano is reading from its own ancient script, following steps written long before human memory. The minerals remember pressure. The crystals remember speed. Even the gases recall their escape routes. Chapter 8. Mount St. Helens' sound beneath the snow. What if silence itself was just another way for the mountain to speak? As winter grips the Cascades, the mountain appears peaceful. Snow smooths the crater's scars, ice fills the gullies, and silence returns. But deep under that calm surface, infrasound sensors record something different, a continuous hum. The sound is faint but steady, a vibration that never fully stops. Scientists at the Pacific Northwest Seismic Network describe it as a living frequency, a tone sustained by the movement of fluids through magma conduits. When magma or gases move beneath pressure, they resonate like air in a buried organ pipe, producing subaudible tremors that ripple for miles. The source remains uncertain. It could be gas migration, magma resonance, or micro-fracturing beneath the crater floor. But the persistence of the signal worries researchers. It means pressure is constant, unrelieved, building quietly while the mountain sleeps beneath snow. Instruments on the flanks confirm tiny deformations synchronized with these sound waves, like subtle inhalations that rise and fall every few hours. To most observers, Mount St. Helens in winter is a postcard of peace, silent, still, and smothered in white. Yet to those tuned to its deeper frequencies, it's anything but still. The infrasound recordings reveal a restless underworld, a steady murmur that hints at unseen motion.
Chapter 9.
Mount St. Helens' unfinished eruption. From the outside, Mount St. Helens appears serene, a white cone against the blue horizon. But to those studying its heart, the volcano feels less like a mountain and more like a living organism holding its breath. The data are converging: rising heat, changing gas composition, expanding reservoirs, harmonic tremors. The volcano that changed modern volcanology is preparing, perhaps not for an explosion, but for transformation. No one knows how long the buildup will last, months, years, or decades. What's certain is that energy is gathering, and history here has a way of repeating itself. For scientists who remember 1980, the unease is familiar. The signs are quieter now, but quieter can be worse. Pressure stored in silence is pressure that will find its moment. The story of Mount St. Helens isn't finished. It's simply waiting for the next chapter to begin. Subscribe for more deep Earth discoveries and updates on the world's most watched volcano, because what lies beneath Mount St. Helens may already be rewriting everything we thought we knew about its calm.